take care till what portion I talked about. But let me, since this is the into the new chapter, let me just go through this once. Uh, so I think these portions you understood, right? I mean, these identical particles, classical distinguishable particles, identical particles in quantum mechanics, and what is the consequence of in case of identical particles, the wave function has to be symmetric or anti-symmetric, right? So these things you know, right?
Yes, sir.
Also, we talked about that these non-interacting particles are subjected to some kind of same potential, average potential they experience, that is termed as V function of xi I, and therefore, the each particle will satisfy a Schrodinger equation, and these are kind of single particle Schrodinger equation. Then they will have solutions. Then solutions generally we tend to write in terms of a productive function. However, if we write in the productive function, there are problems that antisymmetry is not coming out from this. And those are the problems, since the probability is same, whether you exchange won't exchange. So those that relation itself tells you whether it has to be symmetric or anti-symmetric. And therefore, um, you have to consider the wave function in a relevant way, in a consistent manner. That let us consider two particles, as I said, that it could be symmetric. You can write the function, these two wave functions, two particle wave, single particle wave functions. Then you can write in this form. Then it is a symmetric. And if you write in this form, it is antisymmetric. And if these two states are equal, then both states cannot be occupied by more than one particle. And that's why this that is the consequence of the Pauli exclusion principle. If their fermions, in particular fermions, electron is a fermion. Generally we talk about electrons. Of course we talk about photons also in situations, and phonon also in other situations. But as far as these are electrons or fermions, then if you make n1 equals to n2, then these are antisymmetric wave function 0. And therefore it tells you that two particles, two fermions cannot be occupied by a single state. Now, this clearly tells you that the system described by the antisymmetric wave function cannot accommodate more than one particle in a state and Fermi system, the Pauli exclusion principle. On the other hand, the system described with symmetric wave function can accommodate more than one particle, and in fact, no restriction on the coefficient number for bosonic systems that we know. And therefore, in general, if it is a many particle system, for example, how to write the wave function, I mean, anti-symmetric wave function, symmetric wave function, anti-symmetric wave function. So this is the form when there are two particles, then you can write this in terms of this. If there are three particles, then you can have permutations of this I1, I2, I3, and you can have six terms. You can have permutation, and there are six terms, and also be positive. If it is plus sign, then it is a symmetric wave function. Of course, if you change them, then it will return the same thing. However, you can construct the anti-symmetric wave function in terms of this. This is kind of number of permutations, and then pcap operator, permutation operator on this J1, J2, J3. Okay, if there are even number of permutations, then it will give plus sign. If there are an odd number of permutations, it will give negative sign, and that can be represented in terms of this determinant. These are single particle wave functions. And this determinant is called the Slater determinant. Okay, just be acquainted with this, with the nomenclature. This determinant, anti-symmetric function, is written in terms of Slater determinant, and this is the normalization factor. Okay, and in general, this is again, and for n particles, you can write in this form. Okay, so for n particles, you can write in this form. Okay, so this is about the symmetric and anti-symmetric. Now, again, we talked about this, how to count the distinct states, and that I think I elaborately told you, and also probably you asked some questions, and therefore I guess this part is well understood by you. Is that correct, Mosumi?
Yes, sir.
Okay. You don't want me to repeat this one, right?
No, sir.
Okay. So this part is done. This part is done. And then now we are considering an arbitrary potential. An arbitrary potential. Sneak the Chaudhary again and again. Maybe I don't know what is happening. So now consider an arbitrary potential that for which the one particle energies are, are say E1, E2, E3 with degeneracies D1, D2, D3. Think of a system with an arbitrary potential for which that one particle energies are that E1, E2, E3 with degeneracies D1, D2, D3. In general, there are I can write that Dn are or Dn on particle states with energy En. That means the degeneration Dn or the state having the energy En. Okay. Suppose that we have n particles all with the same mass into this potential, a similar particle. Now we are interested in the configuration N1, N2, N3 like this for which there are, what does this mean? This means that N1 particles are with energy E1, N2 particles are with energy E2, N3 particles are with energy E3 and so on. So this is what you are going to say ask. Now, the question is how many different ways can this be achieved? More precisely, how many distinct states correspond to this particular configuration? The answer, of course, it depends on whether the particles are distinguishable or identical fermions or identical bosons. Okay, so whole idea is that you have n particles. Now I want to place n1 particles in with energy 1, n2 particles with energy n3, sorry, n3 particles with energy e3 and so on. Now, of course, I mean total number of particles is n, and then if you want to count the number of states, because the statistics is different, it is different for distinguishable particles, it is different for identical fermions, and also it is different for identical bosons. And then we have to treat them separately. That is what I want to convey here. Now, distinguishable particles. The case of distinguishable particles. Three cases are there. Now, first we assume that the particles are distinguishable. Okay, how many ways are there to select N1 particles to be placed in the first bin? Now, we may choose if there are N particles, we can choose N1 particles in NC N1 ways. Now, one can show this explicitly, of course. There are, say, N ways to pick up the first particle. Then there are N minus 1 ways to pick the second particle, and so on. Hence, the number of ways one can pick up N1 particles is this. However, in this counting, we have counted N1 factorial different permutations of N1 particles. Okay. Therefore, the number of distinct ways is N factorial by N1 factorial N minus N1 factorial. Okay, so this is the number of ways you can choose n1 particles out of n particles, that is n factorial nc n1. Okay, now we have say d1 states in the first bin. Okay, if there are d1 states in the first bin, so each particle has d1 choices, right? And therefore there are d1 to the power n1 possibilities in all, because there are n1 particles. Each particle has d1 choices. Therefore, altogether it will be d1 to the power n1 choices. And therefore, the total number of ways to put n1 particles among n particles in the first bin, consisting of d1 distinct states and distinct options. I would not say yes, states. They're degenerate though, but the energy is same, but they're distinct states, different states. And that should be, of course, n1, ncn1 times d1 to the power n1. And that is what is this. So once you have done with the first bin, then come to the second bin. then how many ways you can put n2 particles in the second bin? Once you have chosen in the first bin, then the remaining particles are n minus n1. Then certainly you have to choose n2 particles out of n minus n1, and then each one has the possibility, to occupy to occupy d1, d2 states, and therefore for n2 particle d2 for n2 probability. Number of ways, sorry, d2 to the power n2 number of ways to fill the state, and therefore you take the product, and then this is the similar as we did in case of first bin, you have done in the second bin. This way, if you keep on filling all the states, all the bins, then you see, then what you obtain is this. This is for the first bin. This is the number of ways, and this is the second bin number of ways you can fill the second bin, and you can just do this. Then this factorial will go up, and d3 to the power n3 by n3 factorial, and n minus n1 minus n2 minus n3, and then again. So these diagonal things will cancel each other, and finally here you will have n factorial and then 0 factorial, because this term will become 0 because you will have no more particle left. Okay, so then if you cancel the terms, common terms in the numerator denominator, eventually we'll end up with this expression, which is n factorial, then in the numerator d1 to the power n1, d2 to the power n2, dot dn to the power nn, and so on, and here n1 factorial, n2 factorial, and so on. And if you write it in terms of product, then it should be n factorial, n equals to 1 to infinity dn to the power nn by nn factorial, n1 d1 to the power n1 by n1 factorial into n2 d2 to the power n2, n2 factorial, and so on. So this is the thing. Can be compact in a compact notation, it could be written in this form. Now, WNN is the number of states of the system corresponding to a set of occupation number NN. You see, this NN, this set, what does this mean? First of all, I guess, you see, do you recall the kind of this Gibbs paradox, removal of big Gibbs paradox? Then probably you divided by something like n factorial, right? Probably that would also come into this picture, but we'll see whether when we will need it. Okay, but I just remind you that in case of Gibbs paradox, you resolve the Gibbs paradox, by dividing this by n factorial. No, so this is the kind of weight factor. This is the number of states of the system corresponding to a set of occupation numbers nn. What does this set means? Means you have a set n1, n2, n3, n4, and so on. You can have yet another set n1 prime, n2 prime, n3 prime, and so on, such that the total number sum over nn has to be equals to 1. Okay, and of course, I mean, E should be sum over nn en. Okay, so because nn particles are occupying the state with energy en, n1 particles are occupying the state in the state with energy E1, and so on. So these things has to be maintained. Then maintaining this, you can have corresponding energy will have, but number of particles is fixed. Then this would be sum over nn, and you can have different states, and for each state you can have a number of ways. You can have the distribution. Now, however, this WNN is a weight factor, and in this case, it is defined as I said, that this n factorial is avoided. Since it's a weight factor, then it is only this part is taken. This n equals to 1 to infinity dn to the power nn by nn factor. So it carries the information about the weight factor. Now, so remember this, okay? So this is the weight factor, n equals to 1 to infinity dn to the power nn and factorial for a set of distribution of particles. So working with the complete distinguishability leads to the probability with extensivity of the entropy, as we have such This is earlier in the form of Gibbs paradox. I just mentioned here. Okay. Now consider particles are identical fermions. Okay, as I said, there are three cases. The first case is distinguishable case that we have already mentioned. Now we consider the particles which are identical fermions. Of course, it is different in which sense. If the particles are fermions, they are identical, they are indistinguishable. It does not matter which particle is in which state. The anti-symmetry requirement means that there is just one particle in one state, and therefore the number of ways of putting nn particles in dn states is given by dncnn, right? Because either a state will be vacant or a state will be occupied by a single particle. And therefore, it has to be dn. You have dn states and you are putting nn particles, then it should be dncnn. So, in this case, now if you uh, carry along the same line as we did in case of distinguishable particles, classical particles, then W, the weight factor, Wnn, it should be product n equals to 1 to infinity, then dn factorial by nn factorial, dn minus nn factorial. Okay, so this is the case for the fermions. Now consider the case of identical bosons. Look, there is no restriction on the number of particles occupying the same state. Now the question is, this is kind of, again, I would say this is again kind of a tricky way of representing as statistical fellows do, okay? A tricky way of solving this problem. Otherwise, it is kind of difficult. So the tricky way is that now basically what is the main problem? Problem is that there is no restriction on each state. Okay? How many particles it will occupy? There is no restriction. Okay. The tricky way of solving the problem is to represent the particles as dots and states. I think I discussed it earlier also, and the states as boxes. So nn particles dots and dn states boxes. Then this problem, that how many ways you can distribute the particles in these states, dn states, the number of ways that can be done by treating it as a statistical problem in a tricky manner by counting the total number of particles and separations. If there are dn boxes, there are dn minus 1 separations, okay, separating walls, okay, partitions, okay. So there are nn dots and dn minus 1 partitions, and altogether there are nn plus dn minus 1 boxes and particles and partitions. Now, if you have a permutation among themselves, then you have total number of permutation nn plus dn plus 1 factorial, okay. But you do not get anything new if you have the permutation among the partitions, and also if you have only the permutation among the particles, okay. That's why you have to divide by, from this you have to divide by the n factorial, that is the permutations among the particles, and also dn minus 1 factorial, that is the number of the permutation among the partitions, okay. So this way you get the total number of ways you can distribute nn particles in dn states if the particles are bosons. That means there is no restriction of putting any number of particles in a particular state in case of bosons. Taking that into account, please remember this is a kind of trick. You don't forget this trick. You will need it at many places. Earlier also I talked about it. Then the way to count the states is basically a permutation of all the partitions and number of particles, and then divide by the permutations among the particles, and divide by the permutations among the number of partitions. Okay, so that way you can obtain the number of ways you can put in n particles in dn dn states. Now, then again, have the same approach. Then you can have a weight factor for the set. That should be n equals to 1 to infinity, and this. So if I bring all them together, the essential information about the weight factor, or kind of number of ways you can you can put the particle, number of distinct possible ways, that is for this for the distinguishable particles, this for the fermionic particles, and this is for the bosonic particles. Having said that, we look at or we go back to our earlier discussions, that the question that we would ask is, what is the most probable configuration? Okay, say, this you see, this value is different for different sets, and what set is the most probable one? Okay, that's the question we ask, and we asked many times earlier also, in random walk case, in canonical ensemble, and others also. In all kind of ensembles, we did ask the similar question: what is the most probable configuration? So we denote that as n star is the one that can be achieved by largest number of ways. Now, it is the particular configuration for which Wn star is the maximum, subject to the condition, of course, n equals to n, and sum over this equals to e. And then certainly we can write, if this is the case, then we can write n minus sum over n equals to 0, and also from this we can write e minus sum over en equals to 0, that we can write. Now you see, so these are kind of two constants we have, and at the same time we have this w. Generally, as I said earlier, is a large number. Generally, they are represented in terms of ln. Okay, ln w. Now, let me just touch upon the maximization of a function, because you see, you have the w with factor, and then you have to maximize it. Generally, in statistical mechanics, since we deal with large numbers, generally we take ln w and then we try to maximize it. But in this case, what we'll do, at the same time, we have to satisfy these two equations, and therefore we have to touch upon the maximization of a function f of, say, f is a function which is function of x1, x2, and so on, of several variables, subject to the condition, say f1 function of x1, x2 equals to equals to 0, and another function, say f2 x1, x2 dot this equals to 0. And maybe there are other functions also. Okay, so f1 is 0, f2 0, and there may be many others, is most conveniently handled by Lagrange multiplier. Okay, so basically what we are going to do here, what we are going to ask is that how can I optimize a function given the constants, say this and this. Suppose there are two constants. In case we have two constants actually, so let us say we have two constants, we can have many constants also. Okay. In general, introduce a new function. You can write a new function which is function of x1, x2 dot dot dot, and lambda 1, lambda 2. Lambda 1, lambda 2 are the parameters, some parameters which are called Lagrange multipliers. You can so introduce a new function which is the function which has to be maximized with the constants f1 equals to 0, f2 equals to 0. Then you add lambda 1 times f1 plus lambda 2 times f2. So you construct a new function this, and then try to set d del j del xn for all n value equals to 0. If there are n xn, then there'll be n such conditions. Along with that, you have two parameters, then it should be two more equations, del G del lambda 1 equals to 0 and del G del lambda 2 equals to 0. If you have n parameters, then del G del lambda 1 equals to 0, del G del lambda 2 equals to 0, del G del lambda 3 0, and so on. This way you will have many equations to satisfy. So here it is easier to work with, as I said, ln of w instead of w. Okay, then we define the function. So you know what we are going to do. So we are going to optimize the function with the constraints. This that means you have to optimize the function in such a way that these equations are satisfied. Okay, that is what we are going to do. Now here it is easier to work with ln w. As I said, it's a huge number instead of w, and then we take G equals to ln of W. Plus, as I said, lambda 1 F1, that is lambda times F1 is basically this because this is my equation. So this plus beta, another Lagrange multiplier is lambda 2 times this one. So this is the new function, and this function has to be optimized, where alpha and beta are the Lagrange multipliers. When W equals to this is a distinct. Now let us, you see this W is different for different situations. I mean, different statistics or different kinds, not, I mean, different kind of particles, I would say. Say for distinguishable particles, it is different, as we have shown. And for fermions, it is different. We have already shown here. And for bosons, this is different, right? So then you have to do look at the optimization, for each case. So distinguishable case W is this. Now I would request you to do this calculation. I will not show you this. I would request you to write G, which is ln W plus alpha times this plus beta times this, or assuming W this, and try to find out what you are getting the relation between this n. So this you optimize. First you write this one and then optimize this, and then you will get some conditions, and you tell me what condition you get, what relation you get in terms of n and d. Okay, do it now. হয়েছে?
স্যার আপনি জি এর এক্সপ্রেশনটা বের করতে বলেছিলেন আলফা আর বিটা দিয়ে, তাই তো?
এই যে এই এক্সপ্রেশনটা বের করতে বলেছি, এন 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 স্টার এইটা।
আমি আবার জি এরটা লিখেছি, একটু থামুন।
হয়েছে?
না স্যার, করছি।
না, এতক্ষণ লাগাতে কথা নাই, এক করো। ও, এর মধ্যে 7 জন চলে গেছে। আচ্ছা, কেন কি ইউনিট করা আছে? অনমিউট, অর্পিতা আনমিউট করা তো, আনমিউট ওই জন্য একটা আওয়াজ আছে। হয়েছে?
ইয়েস স্যার।
আচ্ছা, কে কি বললে?
আমি মৌসুমি বলছি।
হুম। অর্পিতা, হয়নি?
হ্যাঁ স্যার।
ঠিক আছে। So basically, when you take a ln, then basically some factorials are there. Then you use the Stirling formula because number is very large, and therefore you just write in this form and then take the derivative with respect to n, and that itself will give you know, this expression. And alpha is minus mu by kt, and beta is 1 by kt. These are the actually these are the multipliers. Goes one goes with a number of particles, and another goes with energy, and therefore the this is the kind of most probable occupation, because n star is the number of particles occupying per state, because you divide by n and dn, right? So n star, this is, so there are so many sets possible, but this is one set, this is the most probable set. And in case of most probable set, that n star by this dn is the number of particles occupied, or kind of occupation probability for a particular state, and that goes as e to the power minus epsilon n minus mu by kt, right? So if you have, if you ask what is the occupation probability for the state epsilon, it should be e to the power minus epsilon minus mu by kt. Okay. So this is one, and again, I would say that um, if you look at the earlier situations, where most probable one is the most average one, right? So most probable distribution is that corresponds to the average kind of distribution. So probably the average of occupation number, that would turn out to be the same thing. That should be same as this. Okay. Now, in case of identical fermions, you see, then W is like this, and you can do the same calculation at home. So G you can write similarly like this: ln of this W plus alpha times this plus beta times this, and then take the derivative with respect to n star, because you want to see the most probable set of distribution. Then n star will come out like this, and therefore per state, the occupation per state, most probable occupation per state is this, and that is 1 by e to the power, if the energy is epsilon, it will be epsilon minus mu by kt plus 1. This is for the Fermi-Dirac distribution. If the particles are obey the Fermi-Dirac distribution, that kind of situation. And the identical bosons, in that case, you have this, you can work out the similar way to find the most probable distribution, and that again turns out to be 1 by e to the power epsilon minus mu by kt minus 1. You see. So now, if you change the notation a little bit, dn say you express by in terms of gi, nn in terms of ni, and en in terms of epsilon I, then basically we'll have ln w ni is, in general, you can write in this. You can check it, okay? So ln w ni in general, for if you write in a compact form, including all kind of all kind of particles, distinguishable, indistinguishable fermion, indistinguishable bosons. If you take all these into account, then you can have a single expression. You can just write in this form. You can check if you put a equals to 0, whether it reproduces the classical distinguishable case. If you put a equals to plus 1, whether this produces exactly the harmonic case. If a equals to minus 1, whether it produces the bosonic case or not, because you already have all the expressions for all different cases. And note that while doing that, you note the limit ln of a1 plus ax, and a tends to 0, that will give you ax. You cannot simply put 0, right? Then it will diverge. Okay, so you have to have ln of, if a tends to 0, that is the classical case, distinguishable case, then a tending to 0, ln of 1 minus a, and so it should give you minus a times ni by gi. A will cancel and gi couldn't cancel, it will give you only ni. Okay, so you have to do this. Okay, you just cannot straightforward put things in this way. Okay, you have to check kind of limits also. And then if you take this as the kind of combined expression for lnw for a set ni, then you can add you can write down a new function which is lnwy plus say alpha times the number of particles, that constant, plus beta times that constant, and then again you can take the first derivative with respect to n, and eventually we'll find that ni star is basically gi by gi by it will be beta alpha plus beta epsilon I plus a, and number of particles per state with energy I is will be ni star by gi, and that is equals to 1 by e to the power alpha plus beta epsilon I plus 1. Okay, this is the expression. Now you can have the expression for the entropy. Let us see what we are where we are leading. Now you see, if you want to have the expression for S, then S of course is k, then omega n star, because this is the most contribution. Okay, most probable distribution. So you can just the most of the contribution is coming from so many possible states. Okay, so you can just this one, and then S by k is ln w of ni star, and that corresponds to, you have the expression for wn star, and it's this, and then you can just write gi ni, because gi by ni, you have this expression, you can use that. If you use that, you will get like this, and that will give you like this. Summation of ni definitely has to be n. Summation of ni star epsilon will give you e, and other stuff is this. And then therefore you can write this equals to this entire thing is equals to s by k on the left side minus alpha n minus beta e. Now you see, so if you multiply by okay, let us first write it s by k plus mu a, this is mu minus mu n by kt, so mu n by kt minus beta is 1 by kt e by kt, and if you multiply by t in the numerator denominator, the denominator becomes kt, and here it will be st. And g is mu n, you know that gives g is, so g minus e minus ts. Okay, minus plus, and now this one is nothing but pv, right? We have already seen from thermodynamic relations. So this equals to pv by kt. Now therefore we can write pv by kt equals to 1 by a times sum of our gi ln of this, right? Now take a tends to 0. Now we are talking about the classical case. Now distinguishable case, not classical. Then a tends to 0, then ln of, you know that you can write a e to the power this, right? And a cancels, and and what? Sum over gi. So 1 by a, here it is written. So 1 plus x, log of 1 plus x tending to 0 means a is factor tending to 0. It will give this factor, and therefore you can write PV by KT equals to 1 by a, 1 by a sum over gi. Then this is a, therefore minus alpha minus beta epsilon I. Because of sum over gi, a and a cancels, e to the power this, right? And this is certainly, you know, this expression. This is, where is the expression for classical statistics? For classical is ni by gi equals to e to the power minus alpha minus beta, right? And therefore, this is, if you go to the classical statistics, then where is that? The beginning, the first one, this one, right? You see, this is ni and this is gi, and therefore ni equals to gi e to the power minus epsilon minus I minus mu by kt, right? That is what we have substituted here. Here. So gi is this is ni star, okay? Because we have done it for the most probable distribution. Then sum over ni star is of course n. Then you see PV by KT equals to n, and therefore PV equals to n. So it reproduces the classical equation of state for the gas. Okay. So this PV by KT is related to the grand partition function of the ideal gas. Hence, one may expect all the macroscopic quantities from this expression, right? Because PV by KT is related to the grand partition function, and therefore, using the grand partition function, one can, calculate all possible quantities. Okay. So, is there any question on this? Do you have this note with you?
No, sir. এটা পাঠাননি।
এটা পাঠায়নি না? So,
না।
okay, I'll send it right away. And you will get all these things probably in the you will get this in the path 3, you know. So are you following path 3?
Yes, sir.
And how many of are you reading regularly?
রেগুলারলি মানে বইটা পড়া হয় না, আপনার নোটটা মানে হালকা করে দেখি এটাই।
I see. System of ideal particles. আচ্ছা, আমি তো এটা তো আমি ইয়ে থেকেই কপি করেছি আমার ডায়েরি থেকে। Yeah, I'm sending it. My copy. আচ্ছা, সবসময় একটা কাজ করবে তোমরা, তোমরা একটা কাজ করবে, সবসময় একটা বই পড়া ভালো, জানো তো? শুধু আমার নোটের উপর ভরসা না করে নোট থেকে বুঝে নিলে, আমি যেভাবে বোঝাচ্ছি তুমি সেভাবে বুঝে নিলে, বোঝার পরে ইউ শুড কনসাল্ট দ্য বুক প্যাথ্রিয়া, ওখান থেকে আমি পড়াচ্ছি। বাট স্টিল আমি বলবো ফর ইউর বেটার আন্ডারস্ট্যান্ডিং, কারণ আমি বলছি অনেক কিছুই, তোমরা হয়তো অনেক কিছু শুনছো, মাঝপথে তো ভুলেও যেতে পারো। It is always better, যদিও নোটটা আছে, but it is always better to consult a book. In particular, I would, prefer that you follow Patria. বিপ্লব বোলপুর এসছে বলে না? আচ্ছা, অভিষেক আছে? অভিষেক?
হ্যাঁ স্যার।
অভিষেক, আর ইউ অ্যারাউন্ড? অভিষেকও তো নেই। আচ্ছা, দিব্যেন্দু?
Yes, sir.
আচ্ছা, বুঝতে কোনো অসুবিধা হচ্ছে?
No, sir.
বুঝতে পারছো তো? আচ্ছা, এরকম কেউ আছো এর মধ্যে কিছু অসুবিধা হয়েছে কারুর? যদি থাকে বলো একটু। কারণ আমি নেক্সট ক্লাসে, কারণ আবার নতুন করে একটা জিনিস শুরু করবো না এখন। I'll start in the next class. This part I'll start in the next class. Ideal gas, other quantum mechanical ensembles. আচ্ছা, অমৃতা।
Yes, sir.
আচ্ছা, তুমি আজকে আমি যেটা বললাম সেটা একটু সামারাইজ করতে পারবে?
না স্যার, ঠিকঠাক সামারাইজ করতে পারবো না।
কেউ পারবে? সুমন, দিব্যেন্দু?
স্যার একবার দেখতে হবে, ক্যালকুলেশন করে দেখলাম, আর একটু দেখে পরে বললে ভালো।
সমশ্রী?
স্যার একবার দেখি।
Acha. So before you go home, I will just recapitulate once. Dakho, basically you have number of particles and you have states. Okay. Now particles could be distinguishable or indistinguishable. Indistinguishable could be fermions, could be bosons. Okay. Then we want to put some particles in, and assuming that that those states are having some kind of degeneracy, say D1, D2, D3, and so on. Then the main question that we ask, how many ways we can put the particles. Okay, that is the question we ask, and therefore for different situations we calculate the number of ways, number of distinct possible situations we can have, and those are we term as a weight factor, and three cases, three weight factors we have arrived at. And in particular for bosonic case, I would ask you to do remember this, partition box problem. Okay, so this is the kind of tricky way of solving this. Okay, otherwise it is really difficult. You can try, but this is the one which is very tricky way to get the weight factor. Three weight factors we have, and then we have constant also. These are the constants. Then we have to optimize them with the constants. Then we introduce the Lagrange multiplier, and the Lagrange multiplier that comes with this is basically identified in as mu by minus mu by kt and beta as 1 by kt, and therefore you get different distributions, occupation probability actually. All these are known. You have used many places. Probably you have calculated in different way and in different subjects, but here maybe some in some different way. This is the number of occupation number for a particular state with energy En. This is the form for the distinguishable case. For the Fermi-Dirac case, this is this. For the bosonic case, this is this. And in a combined way, you can write the weight factor like this, and then you can have a combined way. You can have represent the average occupation number like this, where A equals to 0 corresponds to your the distinguishable case. A equals to plus is fermionic case. A is -1 is a bosonic case. Okay, these are things, and then you consider that most probable W and start with that and find the entropy, to try to connect with the thermodynamics, and therefore S is this. You can calculate S by K equals to this, and then you just have this and take A tending to 0. Or as such, even without A tending to 0, you can have in general actually, you can have this. You can have these forms. Of course, you use the this Ni star by Gi that you use in terms of your the general formula like this, and eventually you find that that can be written as PV by KT. PV by KT equals to this, and this use the Maxwell-Boltzmann statistics, then it tends to 0. In such cases, it turns out to be sum over n star, and that equals to n. PV equals to n KT. So it does reproduce the equation state of the classical gas. So up to this I have done today, and then we'll meet again on Thursday. Okay.
Okay.
Okay.